Okay, so hello everyone once again. As I don't have much time, I will try to cut it short. My speech will be about ADS-CMT correspondence for Lifshitz-like black holes. So this is the outline of my speech. First, I will start by main motivation behind our research. Then I will quickly mention holographic principle, ADS-CFT correspondence, and then it will be followed by ADS-CMT correspondence. And I will finalize my speech by wave dynamics of Lifshitz-like black holes. So as Professor Sakallı has stated, this is our current research right now. And what was the main motivation behind our research? Well, we wanted to take advantage of black hole physics to obtain more information about superconductors. So why superconductors? Well, superconductors have great many applications in our daily lives. One of them is in medicine. They are used in MRI scanners. And the other one, they are an important part of particle accelerators where great discoveries are being made. It's being used in transportation. Maybe we could ask for further details to our guest from Japan. Apparently it's being used in Japan. So I think this makes life easier, our daily lives easier. And also I have added this application after yesterday's speech from Mr. Karimipur. Apparently they are being used in superconducting quantum computing as well. So this is one of the applications. And the last one, low loss power cables. Well, of course there were many other applications, but I have just listed some of them. As we have zero resistance in superconductors, then they can carry a lot of currents with no loss. They are eco-friendly, it saves space to use these superconductors, and also they are economical. So the only cost for preparation of these superconductors, well, the main cost, let's say, is keeping the material before TC. TC is the critical temperature, which means after this temperature, now your material starts behaving like superconductors. So how could we eliminate or at least minimize this cost? Well, we should try to produce high temperature superconductors. Then things would be easier. So as you most probably know, superconductivity was discovered in 1911 for a temperature below 4 kelvins. Then in 1970s, they have managed to reach 20 kelvins for superconductivity. But for high temperature superconductors, we need temperature to be over 30 kelvins. So the first high temperature superconductors were discovered in 1986, and they were copper-based. They were called Kuiperites, and Bednorz and Müller received Nobel Prize for discovering these high temperature superconductors. And then after a couple of years, there was discovery of iron-based high temperature superconductors, and they managed to increase the temperature by 20 kelvins further. But the highest temperature that was reached so far is around minus 70 degrees Celsius, which was in 2015. So as you can see, we couldn't find room temperature superconductors yet, but if this could be achieved, then this would have many good applications in our daily lives. So this is the main motivation so far for this research. So this picture is for Xin Li from Harvard University, and he has stated that for room temperature superconductivity, which should be around 300 kelvins, we need to conduct more research, and we need to understand what's going on within the phase diagrams, transition temperatures, and these kind of things. So we are planning to use general relativity to be able to discover more properties about these things. Okay, so to sum up, for main motivation, superconductors are energy efficient devices and they have many useful applications. And I have taken this citation from webpage of US Department of Energy. It was stated that unless a material is found that can superconduct about 300 kelvins, we need to apply some cooling systems, and this would be quite expensive. So in this research, we were using general relativity to obtain information about condensed matter systems, but of course the opposite could have been applied as well. So holographic superconductors are interesting in the way that they actually combine different fields of physics. It includes nuclear physics, particle physics, general relativity, quantum field theory, condensed matter physics, and string theory. So this just shows that none of these fields, none of the fields in physics and in natural sciences actually should be over or underestimated, and they're all equivalently and dually beautiful. So most probably you all know about holographic principle. Well, it was first proposed by Hooft in 1993 in a research paper about quantum gravity. And then it was promoted by Leonard Susskind after 2 years, and he was the first one to interpret it from string theorist's point of view. So what is holographic principle? Shortly, it implies encoding n-dimensional information on n-1 dimensional boundary. This is just a short summary. So the most successful realization of holographic principle is ADS-CFT duality, which implies anti-de Sitter conformal field theory duality. And this duality was proposed by an Argentinian physicist, Maldacena. He is one of the most influential theoretical physicists in recent decades. He was the first one to propose this holographic correspondence in 1997 between gravity and field theory. So I have just listed some of the awards that he has received. There were great many. But I just wanted to show you that even though he proposed this in 1997, it was published in 1999, and soon after that he started receiving his awards. And actually there will be a current one which will be awarded on 2019 in May, in a couple of months. So as you can see, this is a quite recent active research topic. And his article that was stating this gauge-gravity duality correspondence is still remaining as the most cited article of high energy physics category. As you can see, it starts from 1998 and it just keeps on continuing up to now as number 1. So after Maldacena, many great scientists have continued to work on this field. One of them was Steven Gobser, other one Igor Klebanov, Polyakov, Witten, and many more. So if we want to talk about the application of ADS-CFT in condensed matter systems, then we can just label this as ADS-CFT correspondence, or if you want to search about this topic, you can just write holographic condensed matter physics. And this duality allows us to compute dynamical transport properties of strongly coupled systems, as was mentioned by many of our speakers today. And condensed matter theories have very few tools to do this, so that's why we wanted to look at this from general relativity perspective. So these are just some quotations from 3 important physicists. One of them, Horowitz from University of California, the other one, Chris Herzog from the UK, and also Sean Hartnell from Stanford. Well, basically, what they are trying to say is that to be able to find how different fields are linked together, it would be a good standing point to search the linkage between these different systems. So in our modeling, we said for simplicity, let us consider 2-dimensional lattices. So in this case, holographic principle states that you need to increase your dimensionality by 1. So the black hole that we have chosen was 3 + 1 dimensional black hole. And this 3 is just increasing the spatial dimension, and 1 stands for the time dimension. So we have prepared this summary so that we can have a bigger picture in our minds of how they correspond to each other. You can think of this as a mapping between the 2 fields. I'm not going to talk about all of them. The most important aspect for us was Hawking radiation, actually. So Hawking radiation for general relativity corresponds to under-reflection processes in superconducting case. And currently there are many experiments that are being conducted in CERN and in many other places as well. So our current article, which is not finalized yet, is entitled as Gray Body Factor of 4D non-abelian charged Lipschitz black hole. Well, this specific black hole was chosen so that it can match with condensed matter theory. We needed superconducting fluctuations, and we needed it to match with 2-dimensional lattice, so that's why we chose this specific black hole. So this was the metric of our choice, and this Z is dynamic critical exponent, where we have theta here, which is hyperscaling violation, and D for us is going to be 4, as it's 4-dimensional. And in 1976, Hertz stated in his article that if you take Z to be equal to 2, then this model describes superconducting fluctuations, and we started from this point. So as I just have 5 minutes left, I'm not going to go into the details, but I just want to tell you that we had scalar field propagating in this background that I had just shown you. So whenever we have spin zero particles, then for analyzing, we need to use Klein-Gordon equation. And this was our field written in separable form. And once we solve this analytically, we obtain a wave function solution. And this wave function can be used to evaluate flux. And then from these fluxes, we can calculate gray body factor. So why is this important? What does this represent? Well, basically, black holes are gray bodies, and it emits some kind of radiation, which is called Hawking radiation. But this radiation is actually affected by the background geometry. And this factor just shows how much your background geometry affects that kind of radiation. So first we find flux at near horizon of our black hole, then we evaluated it at special infinity, and by finding the ratio, it gave us this expression. So as you can see, it was not an easy task. So we are hoping that we can have some experimental verification for this one day by some studies that are specifically on high temperature superconducting systems. So there is a really short video, it's I think 2 or 3 minutes, and I want to end my talk with this video.
Superconductors are materials with all of these amazing potential applications, but the conditions required for them to work are pretty extreme. It's going to take a lot of work to get us closer to a world where we could use superconductors on the daily, and new research has gotten us just a little closer.
But the universe is a hologram? That's one of the most drastic revisions to our picture of space and reality ever proposed. And the evidence for it comes from some of the strangest realms of space. Black holes.
This is a real disconnect, and it's very hard to get your head around. Modern ideas coming from black holes tell us that reality is two-dimensional, that the three-dimensional world, the full-bodied three-dimensional world, is a kind of image of a hologram on the boundary of the region of space. This is a very strange thing. When I was a younger physicist, I would have thought any physicist who said that was absolutely crazy.
Yeah, I think the basic translation between the boundary degrees of freedom, so the ADS-50 correspondence relates a gravitational system that lives in the interior of some space-time with some particles or some quantum interacting system that lives on the boundary. And the basic translation between the two variables is not understood. It's not well, I mean, some aspects are understood and you can compare some calculations, but the general translation formula between the two is not clearly understood. And this becomes even more confusing when you have black holes and you want to describe the interior of a black hole, and then there are even bigger confusions.
The holographic principle only worked in theory at first, with no observable data to back it. But all that changed in 2017, when a peer-reviewed study published observable evidence for the holographic principle. They tested the model against cosmological observations of the early universe and found that the holographic model is compatible with the data that is found in the cosmic microwave background radiation.
Einstein is supposed to have told Lemaitre, he said, "Your math is great, but your physics is dismal," when Lemaitre was trying to explain the expanding universe to Einstein. And I love it because that's often what physicists tell string theorists.
Okay, thank you so much for listening.
Any questions?
I have one question. Why do you have this Lifshitz in the name of this topic? I mean, is he involved in the
No,
research?
not because he's involved, but because the structure of Lifshitz-like black holes with this violation factor just corresponds to superconducting systems. I mean, structural-wise, and properties match with them. So geometrical reasons. I mean, he was not involved himself. So, and I had actually addressed here. Let me show you again the reference for that. I think it was after this point. Yeah. in his article in 1976, he is also mentioning that Lifshitz-like black holes with Z equals 2 corresponds to superconductance. So that was the reason why he chose this geometry.
Okay.
You're welcome.
Yes, thanks to Huriye, Gürsel.